Alrighty, good afternoon, everyone. Um, and we'll go ahead and get started. Uh, so first of all, happy Earth Day. So today is, I guess, the 50th annual Earth Day. Um, and if you remember, relevant to this class, um, Earth Day was actually originally formed out of some of the environmental disasters that we'd already talked about. So specifically the oil spill in Santa Barbara. And so hopefully we can be extra motivated today to learn about these clean renewable energy sources so that we can prevent those kind of incidents from happening in the future. Um, okay, so before I begin with lecture, a couple logistic items. So as a reminder, homeworks are due at the end of the day today. Um, and then homework 2 is actually posted, as well as a practice midterm. And so it's probably a good idea to go through the practice midterm before the actual test. And we'll actually cover the material on the practice midterm next Monday. So please work on that before then. And then lastly, the project groups have been posted on Canvas. I made an announcement on that. So please make sure to check in with the other members of your group, which you can do via Canvas. You should be able to message anyone else in the class. And so, get each other's contacts and then reach out to each of the energy mentors. They're not going to be responsible for, keeping you guys on the deadline. So, make sure that you're going to, that you submit all the required materials for the project, including the abstract, and then the outline, which will be interim before your final presentation and project reports. And all those due dates are in the syllabus. So you'll definitely want to make sure to meet with your energy mentor sometime soon so that you can get the project started. Okay, so there's a question: is the midterm going to be proctored using Examity or ProctorU? So I think that those are those the ones where you have you're viewing people on camera? Because if that's the case, that's not what we're going to do. It'll be more of like a take-home exam. So it'll be essentially an assignment that you have a shorter amount of time to do, and it's open computer, obviously, because I can't stop you. But we'll try and organize the midterm in a way that's sort of accommodates that. There's a question: where can I find my group mates again? So that's posted on Canvas in an announcement. There's an Excel file that I put together that basically lists what project you are in, as well as all the projects for each individual. And then it gives the name of your energy mentor and their email for contacting them, of which actually I'm one of the energy mentors. So I'll have somewhat of an idea of when you guys reach out, because one of the groups has to reach out to me, which I haven't heard from yet. So please do make sure to reach out by the end of the week. For the energy mentors, they're all really cool people. They're volunteering their time to do this, and they're really knowledgeable about the energy topic, and I think pretty excited to get you guys engaged as well. So please do make that the effort to reach out and get engaged with the project. Okay, there's a question, do we reach out as a group or individually? So definitely reach out as a group. Make sure that you have talked to all of your colleagues that are in the group. And then so that you can make sure that everyone's on the same page in terms of scheduling and all of that. So do email them all together. Someone's saying they don't see it in the announcement. I think it should be there. I would double check. It is also posted under the files. If a lot of people are having trouble finding it, you guys can like message me on Canvas or email me, and I'll double check. But I think that some people have already been able to find it. So look a little harder. Okay, so I think that's it in terms of logistics. I guess there's one more issue separate from the logistics. So sorry about what happened last time, and then hopefully that won't happen anymore. I think that issue was resolved. There was actually a secondary issue with my laptop running out of batteries, even though it was plugged in. Okay, sorry, the questions are like streaming in chat, so I'll just take them as they come. Are you going to post an answer key for homework 1 so we can look at it? Yes, I will. We already have a solution set written up. So actually, when we grade them, we'll provide these little template sheets back to everyone that not only gives your grade but a little bit of feedback. You know, if you did a problem wrong, we'll sort of indicate what went wrong, but you can also look at the solution set to understand how to approach the different problems, especially if you got one wrong. Okay, where was I? Okay, yeah, so a student had reached out to me about the format of the lecturing, which I totally understand. You know, it's challenging for some people. You know, a 2-hour-long video lecture is definitely a pain. Like, I can barely keep my mind focused on a 10-minute YouTube video. So I get it. It's not ideal, but in terms of restructuring, I think that I actually got a lot of feedback from a number of other students who said that they thought that the format was fine. So we're gonna keep doing it like this. Sorry to those who find this, you know, particularly challenging. It's definitely an unusual format, so I sympathize. But I think we're going to continue with doing the slides and the longer lectures. I would say, you know, if you guys want to be more engaged, I'm all for that, and we're definitely able to like dive in deeper to topics. Just feel free to like chime in either through chat. I know it's a little harder to speak up in this format, but you are definitely welcome to. And so the more interactive portion, I guess, is kind of up to you guys, and I'm happy to have that sort of back and forth. But generally, we're going to keep to this format, and I'm not going to be doing more sort of condensed pre-recorded lectures. Okay, another question coming in. So I was also wondering if you'd be posting a formula sheet. Yeah, actually, if you go ahead and if you look at the practice midterm, that already has like a reference sheet. So as we've been going through a lot of the lecture slides, you know, every now and then, you know, I've had sort of these like reference slides that have, you know, conversions and efficiencies, that sort of thing, and all that reference material. You know, so first of all, when you actually do the midterm, you're welcome to go and look at that stuff. But I actually have included that, a lot of it, and a lot of what I think is necessary in in the actual midterm itself. So like the first 2 or 3 pages are just sort of tables and equations of reference material. There will be some things that you can like just look up online. So I think on the practice midterm, I have some questions about California where you might need to know like the population of California. And so, you know, that's open for you guys to look up. And in fact, like probably I don't think any of you guys will do this, but you know, some of the numbers on the reference sheet can vary depending on the source. Like just as a hypothetical, it's not on the practice midterm, but it potentially could be on the actual midterm. I don't know yet because I haven't written it. The lower heating value and the higher heating value, right? Depending on when you get that source, that number could be different at different times and from different sources. So as long as you cite your source, that's totally fine. And like I wouldn't dock any points for it being different from like a reference value provided in a lecture. It really doesn't matter to me. So yeah, keep that in mind. We'll be pretty open-ended in terms of grading and the like values on the midterm. It's more important to me that like it's not that like you get the exact number right. It's more important that you understand the concept and think about why it's important and all that sort of stuff. You know, looking at this class isn't about memorizing numbers and memorizing equations. Okay, and so with that being said, here are a bunch of numbers and rough references. So picking up where we left off last time, we were talking about a lot of the the theoretical potential resource availability. So we had gone through solar, wind, and hydro resources. And here we're gonna sort of quickly polish off the end of last lecture before it crashed, and think about some back of the envelope stuff for biomass. So again, these are some reference numbers that are you know, rough estimates, and you can keep in mind to get like rough order magnitudes for things like, so good biomass energy crop growth, you're getting about 20 dry tons of crop per hectare per year. So it's essentially, you know, given some amount of land, this is how much you can grow. We can convert the dry tons of that crop into biomass energy. And the number here is approximately 18 gigajoules per dry ton. You know, that whole sort of production cycle requires some conversion into a more usable form of biomass. And so you do have some efficiency losses. So you can see that in the technology application below. But even below that, in terms of the energy content of the biomass itself, I can convert the gigajoules per dry ton into the amount of energy per year by multiplying the top number and the middle number, so 20 times 18, and then I can just convert it to kilowatt hours, for example. So biomass can be burned as to produce electricity in certain types of devices. So it would be really pretty similar to probably the steam turbines. So instead of burning coal, you're just burning biomass. It's probably a lot less efficient, unless you have a plant that's sort of specially calibrated to be able to handle that. You also can convert it to fuel, and so they turn the biomass into liquid fuel. I actually got into energy side of things when I was an undergrad. I sort of moved from a more biology major into energy, into an energy degree, because I started working at a at a biomass wet lab where we were making uh, ethanol from cellulosic biomass, and so this is basically taking plant material and converting it into like a liquid fuel that you can use to burn. It's a pretty interesting process, and so nowadays I'm more sort of on the engineering side of things, but a lot of the work in this field can actually be more in sort of like chemistry, biochemistry sort of field. Okay, so one thing you might be wondering is like, wait, hang on, we burn biomass, so how is that a renewable energy source? So if we go ahead to the next slide. So despite this being sort of combustion, the reason why we think about this as a renewable resource is, unlike fossil fuels, which are coming from a set amount of fossils that have been formed in the past and undergoing sort of chemical and physical changes to become oil, coal, and natural gas. With biomass, this is sort of a continuous cyclical process where you take plant material, you combust it, but that the plant material can be sort of regrown, and actually the balance is fairly robust, right? So the combustion of the biomass will lead to emissions of water and carbon dioxide into the air. But the growth of the biomass that you use to produce the fuel is taking in carbon dioxide and water. And so even in terms of like climate change, biomass is a nice system in that it uptakes a lot of the things. It uptakes basically the same volume of carbon dioxide and water that's emitted from the combustion. Well, I shouldn't say same volume. It's a little bit different, but for most intents and purposes, in the sort of order of magnitude, you're looking at a pretty nice balance, as opposed to fossil fuels, which is like carbon buried in the ground that we're sending up into the air, right? So that's not something that gets balanced out. What's the best place to grow biomass? So this is similar to the maps for like solar and wind and hydro. We can have sort of resource availability or potential. And for biomass, it's talking about yield potential, and we can generate these sort of maps as well. And so you can see a lot of the best potential is kind of in the Midwest area. In terms of the current resource availability, in other words, like where we're actually growing a lot of the crops that we use for biomass today, that's coming in this map. And so a lot of the biomass is a variety of feedstocks that can include things like corn, soybeans are actually a big one as well, and there are some sort of controversies regarding different types of food stocks, especially as they compete with food sources. And so there's a big movement, or there has historically been a big movement of using sort of types of biomass that are less competitive with things like food. And so that might include something like switchgrass, which doesn't directly compete with food resources. And we'll talk a little bit more about those externalities once we get to sort of the environmental and externality impacts about different sorts of renewable resources. Um, for energy potential, some people have calculated a rough upper limit for global biomass. Yeah, okay, there's a question here. So why wouldn't it compete with resources if it still takes up land? Yeah, so that's a good point. So when I was talking about growing something like switchgrass in the place of corn, um, yes, it would still take land, but there are some sort of key differences um, in that the demand of the crop itself won't get shifted in a supply sense, but also the density of different biomass could take up different amounts of land, and you can grow them in places in different places where it wouldn't compete. So you know, certain types of plants will grow in areas, for example, that you wouldn't normally grow food crops. So there definitely still is some aspect of competition in terms of using like land resources, but it's mitigated from a whole slew of these things that I was just talking about. Great. So then the calculation for the upper limit is about 3,500 exajoules per year. But again, there's lots of competing uses for land. So this is sort of like if all sort of arable land were just being used to grow biomass. But in reality, right, we use land for other reasons, and we use it to grow food as well. So the actual sort of more technical limit and economic limit is going to be way lower. Yeah, and we'll get into that momentarily. So that kind of wraps up the end of last class's lecture. And today we'll talk about, if you recall, the different other sorts of potential, so technical potential and economic potential. And so here we get to learn a little bit about how the actual technology works. And that's going to help us get a sense of the technical potential, because we'll understand about efficiencies and how technology is actually able to use the energy resource. Okay, and so the technical recoverable potential of direct solar energy. So in this same slide deck, when we talked about the theoretical potential, you can go back and see that this number is now pretty different, because now it thinks about so the different levels of insolation. In other words, that's kind of the amount of energy per meter squared, and it's looking at the ability of our solar technology to capture that. And it thinks about other factors, dust and weather, and how these things specifically affect not only the solar insolation, but also the efficiency of the technology. So when I talk about solar energy, probably a lot of you guys have in mind the applications of it through, you know, your solar panel, right? So solar photovoltaic. I think that's what most people sort of immediately think about when you say solar energy. But actually, there are lots of pretty neat applications of solar that extend well beyond that, and can actually functionally be a really important contributor for reducing, you know, energy consumption, or making energy consumption a lot more efficient. So there are a bunch of passive uses, things like space heating, cooling via reflection, and daylighting. And so even some people even consider something like an awning for a window as a sort of way of manipulating solar energy, right? And you're cooling your house down without using any energy at all. And that can be, in fact, a really quite efficient way of reducing energy use. Hot water heating and cooling. there's actually a pretty neat way of leveraging solar energy to take advantage of water heating and cooling systems, of which I'll show a diagram in a second. And then there's actually analogous to the way like a coal plant works to boil water. There are actually types of large utility scale solar plants, which again we'll look at here in a moment, that essentially, instead of absorbing the solar energy in a photovoltaic array, it actually reflects it using just a mirror. And it can concentrate the solar energy to boil water and essentially run a turbine. And then the last one is electricity production through photovoltaic, the traditional one that most people think of. And so we'll go through all of these sort of different technologies. So one of them, solar cookers. And so this is using reflector mirrors and sort of focusing solar energy to get hot enough to actually be able to cook. So you might think that this is like kind of silly, kind of niche, like we wouldn't really do this. It'd be really a big pain, right, to try and cook with one of these devices when we just have a stove at home. But in actuality, this is a really big and sort of useful contribution in developing countries, where a lot of the cooking is done with wood burning stoves. There was a big project actually at UC Berkeley, where they were looking at trying to reduce wood usage from stoves, because actually in a lot of areas, so this was actually about a decade ago, when you had problematic conflict areas in like Darfur, where it would be dangerous to actually collect wood, because you wouldn't want to go out to certain regions, and having like a solar cooker would alleviate the need to collect that fuel. It reduces the cost to a lot of the families of collecting that fuel, and it reduces a lot of the like really harmful impacts of these wood burning stoves, which are usually indoors, and you have extremely high concentrations of particulate matter from burning. And so these things are, we may view them as kind of silly and niche, but actually can make a really significant impact on the lives of folks who are, spending half of their income on fuel for cooking. So yeah, solar cookers, pretty neat, cheap, handy invention that can have a pretty significant impact. Solar heating systems. So these are pretty nice devices that can integrate in with the your water heaters at home. And so the way this works in a traditional home, right, is you have this sort of big tank of water that's heated, and so that allows you to do things like, take hot showers. And usually these water heaters are powered by combustion of natural gas. They can also be electrically heated, and all of that takes additional energy. So in this case, you can have these solar heating systems which take in energy from the sun to heat up water in this little exchange tank. And the reason why you have this exchange tank is oftentimes that the sunlight doesn't actually have enough energy to get the water as hot as you would like. And There are actually types of solar collectors which will sort of do the existing one, but they might have like a much larger footprint, or they might be a lot more expensive. So it's actually more typical to have an exchange tank. And so in this exchange tank is you actually have um, uh, slightly warm water, not quite as hot as in your existing water heater. But what that does is the amount of energy needed to heat already warm water is significantly lower. And so this improves the efficiency. It's going to lower your bill for either electricity or for natural gas. And so this can save a ton of money over time. Okay, so now let's talk about the sort of more traditional one. This is a little cross-sectional diagram of a solar photovoltaic cell. So the way this works, the PV cell is a type of semiconductor, and it's got negative electrodes and positive electrodes. Sunlight comes in, and the photons will impact the cell and sort of, quote unquote, sort of dislodge an electron. And it goes through a circuit here to create electricity because it wants to bond with your positive electrode. Well, okay, I guess it's kind of the reverse of that, but yeah. So essentially, the sunlight is going in, exciting the electrons, and then passing through a circuit to create electricity. And that's basic. That's sort of the basics of how a PV cell works. They're designed by essentially doping silicon with boron on the on the positive side of your electrode, and bonded with phosphorus on the negative side of the electrode. How efficient are these things? So what that means is, if I were to think about the energy content of an excited photon, and I were to transfer that into my PV cell and move that through my circuit, the highest sort of recorded efficiency level is about 46%. But on average, the sort of PV cells today are operating between 15 to 20% efficiency. And note that is like a different metric than when I'm talking about the capacity factors, which is like how often sun is shining on this. This has to do with the actual energy content transfer between the photons and what you're getting out in electricity. The individual PV cells themselves are pretty similar across most of your PV technologies, but the scale and magnitude and size of a solar array can be pretty different. So on the left side, we have what's called utility scale. So these are things that these are things that something like PG&E might own, or well, okay, not PG&E, but a generator that or a company that sells electricity to PG&E. I see a question, where do those 85%? I'm not sure I understand. Maybe do you mean where is the 85% of the energy lost? Yeah, so if you think about sunlight hitting a solar panel, it's not necessarily just the like loss in an individual photon. It's like the amount of energy in the total flux of light hitting it. So if you look at a solar panel, it doesn't just absorb the light. You see some reflection, right? And then if you put your hand over a solar panel, I bet it's also pretty hot, so some of it gets lost as heat. So reflectivity, and then absorption of the materials as heat. That's all sort of some sort of energy transfer. So you're getting you're losing efficiency in that way. Yeah, okay, so utility scale, and then what we call as distributed solar, that is stuff that might be on like a rooftop, so localized. And distributed can refer to sort of behind the meter, and that's a concept where if you think about how your electricity use is measured, they have utilities have these metered devices. It used to be that they would have to go out and read them manually, but now we have smart meters that transfers the information to the utility directly. And so when it's behind the meter, you get this thing called net metering, where the amount of energy that you're collecting from solar is like canceled out against the electricity that you're pulling in, and so that's called net metering, and that's a pretty important concept for solar, and we'll probably talk a lot more in detail about this when we get to some of the policy section lectures and how they relate to getting these things to be particularly useful for consumers, and have consumers be able to take advantage of how these are integrating in with our electricity system. Okay, who is building solar? So by far, the country that's accelerating for installations is China. They're putting a lot of resources into expansion. But as I mentioned before, renewables are definitely the largest source of increase in new capacity. So you can see that being reflected here in terms of gigawatts. It's a fairly large amount of capacity that's getting added. Again, just as reference, 50 gigawatts is the peak electricity demand in California. So, on the hottest day when everyone's running their AC, it's equivalent to about the total amount of solar that is produced in across the entire United States. So decentralized versus centralized, this is what I was talking about with the distributed versus utility scale. So having them sort of on your rooftop versus having the larger sort of solar farms. So in the orange is the more sort of solar rooftop ones, which originally was sort of the biggest source of this, but then over time, the more larger solar farm resources have grown quite a bit. Okay. So now let's talk about a slightly different technology. So this is concentrated solar power, also known as CSP. I'd mentioned before in one of the previous lectures that to generate electricity, we just basically want to get things to spin, right? So if we can get things to spin, we can turn a generator and produce electricity. So solar photovoltaics are one of the few things that doesn't actually require mechanical movements. Basically everything else does. And even with solar, you do have ways to manipulate it such that we are still actually turning a turbine. And so in this case, a CSP is quite different from a photovoltaic system in that it doesn't try and absorb any of the energy directly in these panels. The panels are actually just mirrors. So they're super clean mirrors that reflect the sunlight with a high degree of efficiency, and it focuses all of that energy onto a really small area to heat up and actually boil water. So so that water goes through, the steam drum, passes through a turbine to, spin the generator and produce electricity. So in principle, it works, pretty similar to a, coal plant or a nuclear plant in that it's doing energy generation through an intermediate of a steam turbine. CSP is definitely like quite a bit smaller, right? So if you remember in the United States, that the number was about 50 gigawatts for solar PV. For solar CSP, you're talking about on the order of like 1 to 2 gigawatts. So definitely smaller. Spain has an appreciable amount of CSP relative to most other people, but still overall a fairly small amount. Okay, so that sort of wraps up the solar part. Let's talk about the technology of wind turbines. So this one is definitely one of those ones that you get things to spin to create electricity. And the turbine is in itself this entire sort of technology device. And you are spinning a giant rotor blade, which essentially rotates a gearbox and spins a generator to produce electricity. The sort of top box up here is called a nacelle. It's a little room that actually you can have people come up into it to do maintenance. It's a fairly arduous process. These things can be quite large, as you'll see in a moment. But you can go on the inside, and they have like a series of ladders and platforms that you can climb to get to the top. Yeah, the people who do maintenance at wind farms are really, really fit because they're climbing up and down these turbines basically all the time. The theoretical maximum efficiency of these sorts of wind turbines is around 60%. And on average, we're extracting more like 35 to 45% of the energy of the wind, which is actually, I think, pretty high. So why are wind turbines really high? If you'll recall from the theoretical potential chart before, in last lecture, basically at higher elevations, you're getting higher wind speeds. So there's more sort of essentially energy available to collect. Oh, sorry, I saw a question that I missed. So there's a question: why is solar CSP less popular than PV solar? I think that to make them economically competitive against PV, they have to be sort of in the right conditions. And the other thing is that if you've ever seen a solar CSP farm, it actually takes up like a really large amount of land, and so usually they're located out in the desert. There's like one big one way out east of Los Angeles in like the Palm Springs area, I believe. And yeah, so I think there are a number of factors for why they're less popular, and usually it has to do with the economics of it. Okay, so in terms of the wind energy, we can calculate this based off of the kinetic energy equation. So 1/2 mass times velocity squared. You can convert the mass of air into using this equation, right? So if you think about the surface area that the wind passes through, so that is the like circular diameter. So if I were to just draw that really quickly, again, so if this is my wind turbine, my blades might look something like this, and it's spinning. So this area is what we would be measuring in this equation for A. So it would be the 1/2 the diameter times pi squared, right? Pi r squared. Okay, and then if you have the density of the air, the wind speed of the air, and some amount of time, then that will tell you essentially the volume of air that passes through the wind turbine, and that simplifies to this equation. And so that's the amount of wind energy, and then you typically multiply this against an efficiency. So this whole part would get multiplied by maybe some efficiency mu, where mu is equal to efficiency of wind turbine. And then in the calculations, I think it would typically be given to you, but it'd be pretty safe to use an efficiency of about like 40% or so. Okay, so moving on, there's actually tremendous variation in the size and scale of these wind turbines. So back in the early 80s and 90s, you are talking about wind turbines that are about 20 meters high, right? Still pretty big, right? This is like the size of a five or six story building, and they've just sort of progressively gotten bigger and bigger over time. And the amount that the capacity obviously increases, right? Because you're capturing more wind energy. Actually, even in my mind, when I was in grad school, sort of the biggest wind turbines that I had been hearing about were like 3 megawatts, which is a tremendously large, right? This is as tall as a football field, with massive rotors that are several stories tall, essentially. And these can generate so 3,000 kilowatts. So a single wind turbine could power, when it's running at full bore, it could power essentially 3,000 houses, right? So quite a lot of energy. But even now, apparently there are turbines that get up to 5 megawatts, so 5,000 kilowatts, and these usually are ones that are offshore, which means they're out sort of in the ocean, where there are more sort of wind resources available. So who knows how big they'll get in the future. And just to give you a sense of scale, right? So the average onshore U.S. turbine, so 466 feet. So that's actually a little bit bigger than a 100-meter one, right? And so this is taller than these wind turbines are taller than the Statue of Liberty. The largest turbine in the world, I believe, is this one, the Haliade X, made by General Electric. These are for sure offshore wind turbines. So 853 feet. That's actually bigger than this, I believe, or probably comparable to this one that they're showing in terms of future. It's almost as tall as the Eiffel Tower, and you can see how it compares to like the Empire State Building. Pretty large. One of the interesting things is that so this may be kind of obvious, right? So as the turbine gets bigger, as I was showing, the capacity gets quite a bit larger. Okay, there's a question, does the size of wind turbines, is that relative to the conditions and the environment? Yeah, exactly. So you're going to be designing wind turbines to be put in specific areas where at this height, it's sort of optimized to be able to capture the 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 highest sort of wind currents. So they definitely take that into account, and you don't just build like the biggest one possible and stick it anywhere, right? So a lot of the really big ones only make sense to put in the ocean. Um, yeah. Oh, yeah. That's right. So Facundo's pointing out the logistics of installation is also a limitation. I don't know if you've ever seen uh, like videos or even in person of the transportation of like the blades. They are on these massive trucks, and it can be tricky to get them to the area that you need for sure. Um, so it may be kind of intuitively obvious that as the turbines get bigger, their capacity increases. In other words, the amount of energy that they can produce for a single turbine increases. And we can see what that trend sort of looks like on average for wind turbines over time. So we can see the height in red, the size of the rotors. So basically the blades, the diameter is getting larger. And then the nameplate capacity in these blue bars continually increasing. Okay, and so that kind of makes sense. One interesting thing that I actually found was pretty surprising. I didn't know this until I was making these slides, is that the capacity factor also increases for wind turbines over time. In other words, they are better able to utilize and capture the amount of wind passing through. And so this is both a combination of efficiency. It's probably also having to do with uh, placement of the wind turbines in better and strategic locations. But it's pretty interesting. Over time, the capacity factor of wind turbines has increased as well. Um, so wind power in terms of global capacity and annual additions. Um, so so wind is definitely sort of at least for now quite a bit larger in terms of capacity amount than solar, and we can see um, how that has grown over time. And so in the yellow is like the last years, and then the orange is the addition in that year. So you're adding something like the so 50 gigawatts is basically the total amount of solar uh, in the United States getting added basically every year. But do keep in mind that this chart is global. In terms of offshore, so this is offshore is all the stuff in the ocean. That is smaller for now. So we look at the cumulative offshore wind capacity. It's about 18 gigawatts total, as opposed to onshore. Well, this includes both onshore and offshore, but total, most of it is onshore wind, and that's closer to about 600 gigawatts. But again, growing pretty quickly, and similar trends with most of the renewables. We're talking about rapid growth over the last decade, and essentially what that means is we're slowly but surely offsetting other forms of electricity generation. Um, for offshore, a lot of that development is happening and ongoing. So here is a little chart of existing plans to develop offshore wind along the East Coast. There are a lot of different companies and a lot of different projects that are looking to build out in these areas. And there are similar types of things that you could find on the West Coast. It's not, I think it's not quite as developed in terms of volume on the West Coast compared to here, but nevertheless, lots of offshore wind up and coming. Okay, before I move on to hydropower, we're halfway through, so why don't we take a quick breather here? Um, yeah, and in the meantime, again, happy to take questions either on the material that we're talking about today, or if there are any things else about the class you want to talk about. Um, let's see. Okay, there's a couple questions coming up. So the first one, when we talk about biofuels being carbon neutral, is that accounting for soil carbon losses from tilling and agriculture practices? Um, no, people usually talk about, when we say carbon neutral, it's usually about carbon in the atmosphere. There is a huge, really, I really do mean huge amount of research and work and literature on impacts of biofuels and biomass development for land use. And that's a really big topic. It's not only about carbon in the soil, but also things about agricultural practices. What are like sustainable ways of doing that? I'm not so familiar with that field, but for sure it's something that people think about. And in fact, that is one of the probably bigger points of drawback that people point against biofuels is that it oftentimes has negative implications for land use. There's another question, when will the project abstract be due? So I think on the original syllabus, it was due today, but I think I pushed everything back because there was a delay in getting all the project descriptions out. So I would check the syllabus again. That date has been updated. I can actually, I'll just quickly pull it up so that we're sort of all on the same page. Um, so the initial abstract is going to be due not today, but 1 week from today. So you definitely have to talk to your mentors by then and put a little something together. Okay. There's a question about the midterm next Wednesday. Do we still have a lecture on that day? No, actually. So there's not going to be a lecture on that day. It'll be an off day to just work on the midterm exam. So I think what I'm going to do for the midterm, it's not going to be a strict like 2-hour time limit or anything. You guys are free to work on it over the course of a day at home. So what I'll actually do is we will release the midterm on Wednesday morning in place of the lecture, and then 24 hours from then 10 a.m. I guess or sorry, not 10 a.m. 12 noon on Thursday we'll have it due. So you have 24 hours essentially to work on it. Yeah, and I will make an announcement about that because I guess I haven't really talked about the logistics of the midterm yet. But essentially it'll be a one-day take-home exam. Do I know what the format will be? I'm not sure what you mean. It'll be a test. It's not like multiple choice if that's what you're asking. It'll be like you know, short answer where you're working through some math. You know, there might be some like essay question type things. But yeah, it'll just be, you know, a typical take-home exam with a bunch of questions. The midterm will cover material through today. That's right. Yeah. Yeah. So again, the examiner, it's not going to be multiple choice. It'll be calculations and short answers. Yeah. Alrighty. So let's continue on. There's actually quite a few more slides to get through, so I might have to accelerate a little bit. I actually thought that I would run short across 2 lectures, but it looks like it's going to be running long. So hydropower potential, largest. It's currently the most renewables that we're using is hydropower. That accounts for about 15% or 16% of global electricity production, about 3,000 terawatt hours. It can be generated using large dams or smaller hydropower plants or pumped water storage. How these work, same sort of idea. You get something to spin, right? And so they have hydropower turbines, which we'll show some examples of. Essentially, you're taking advantage of the potential energy of water wanting to go from high elevation down to low elevation. So you can imagine that there's a lot of water pressure sort of down here compared to up here, and that pressure is essentially what's getting this turbine to spin. Spinning the turbine spins a generator, creates electricity. So same principle. We can, oh yeah. Let's see, okay, there's a question. Can we have the project abstract due a day after the midterm? Yeah, I guess there is a little bit of overlap there, huh? Yeah, that's fine. We can, yeah, we can be flexible about that. In fact, maybe I'll just have it due at the end of the week next week, so we can turn it in at the end of Friday. That'll give folks a little bit more time to reach out to mentors and talk to them and put the abstract together. I will post an announcement about that, and then yeah, you guys, for anyone who's you know, just catching up on lectures, you can have make sure to like tell your group members that we'll push that back. That's fair. I guess I didn't look quite closely at the calendar when I pushed everything back 1 week. Yeah, so we'll have it due next Friday. Facundo, can you remind me to make an announcement about that?
Yeah, don't worry.
Thanks. Cool. Okay, so power from hydro. This is, if you look at this equation pretty closely, you'll notice that this is actually just MGH, which is the equation for potential energy. So we got our kinetic energy out of the way with wind. Now we're doing potential energy. So it's equal to the mass of water, which is the density of water, which is rho, times your flow rate, right? And then the head is just the height in For power plants, they refer to that as the head. I guess that's the sort of proper nomenclature, and that's the height between the inlet and the outlet surfaces. You've got your gravitational constants, and in this equation, actually, this already has the efficiency of the turbine included. I think so. Again, when you think back to the kinetic energy equation for wind turbines, that didn't have the efficiency. In this one, it does. But again, conceptually, right? It's just kinetic energy times the efficiency of the turbine, and here it's just potential energy times the turbine efficiency. These are some examples of the different types of turbines that are used in hydropower facilities. There's actually quite a few, and beyond these as well. You don't have to know necessarily the right the specific like mechanical engineering sort of details of why you choose one over the other. But I will say, the efficiencies of these different turbines will depend on the head and the flow rate. So in other words, like if you have a really big dam with low flow rate, or if you have a really high dam with low flow rate versus, smaller dams that have varying flow rates, these different turbines are optimized to be utilized in different applications. And so here is a little chart of differences in flow rates and differences in heights in the head. And this is a little diagram of like where different sorts of turbines are located in that height versus flow dimension. So, the Kaplan turbines are usually low flow, low height, whereas, Francis turbines span more of the higher flow, high height, and Pelton turbines are low flow, but large head. So that gives you some perspective about how we can apply different sorts of turbines in different conditions for hydropower. There's another type of hydropower called pump storage. So this is a little bit different in that it's not sort of just taking the natural flow of water from high to low elevation. You actually have two reservoirs, one low and one high, and this is essentially a storage device. It's like a battery. Essentially, you are when you are generating electricity, it's pretty much this same diagram as before, where you are taking advantage of the height difference, getting the pressure to spin your turbine and creating electricity. But in this case, there's actually also a pump, which is able to pump the water from my low reservoir up to the upper reservoir. And that takes electricity to pump and bring the water up. But then that allows you to store essentially potential energy in the form of a water at high elevation that you can then leverage later on. And so this is a pretty nifty sort of feature of hydropower that really isn't available in any of the other sort of energy generation forms that we've talked about before. And we'll discuss a little bit more about energy storage later on, and how that relates to integrating with the electricity grid, why we would want to do something like this. So one of the things that we've talked about, for example, just really quickly, the intermittency of like solar and wind. Well, if we have too much solar power, you don't want to just get rid of it, right? You'd rather put it into storage. So you could actually use the excess solar power to, for example, operate a pumped water storage, send water up, and then later on at nighttime when you don't have solar running, you can, for example, take advantage of the electricity that you've essentially stored as potential energy. In terms of total hydropower, we can see the development and resources by country here. I'm gonna sort of breeze through this for sort of the purposes of time. You can see the historical increase over the last couple decades. in places like the United States, we have essentially saturated a lot of of the resource that's available. So it's pretty hard to expand hydropower. So unlike, you know, a natural gas plant or coal plant where you just build it and then you provide the fuel, or it's, you know, solar and wind where you're finding areas that there are still lots of areas that have the resource broadly available. Hydro is kind of used up, at least in the United States. But in a lot of the developing world and in places like in China, which has really sort of, again, sort of started pursuing renewable resources, they are expanding their capacity quite a bit. And they actually have a large amount of resources available. Okay, so that that wraps up hydro. So moving onwards to biomass. So the applications of biomass can be found in heating, right? Just burning it. Electricity generation. So you're using the combustion of the biomass to spin like a turbine. And then production of liquid biofuels for transportation purposes. So thinking about complementing gasoline with ethanol, or even substituting away from traditional fossil fuels. You might do that with biodiesel, for example. The use currently, right, with so this is the technical potential now that we're talking about, 50 exajoules per year. The vast majority of that is for non-commercial fuels. So we've talked about this before, wood burning for heating and for cooking, and also you know, crop residues and dung for combustion for sort of the same purposes. When we think about sort of more modern biomass use, oftentimes that's right, converted to other forms for things like process heat, for electricity, and for fuels. And that accounts for about 20 exajoules per year. And of that 20, you've got about 10% of that for transportation fuels. So that should give a sort of rough order of magnitude understanding of how biomass is kind of used today. The thermal conversion process, or sorry, the biomass conversion process spans a number of different conversions depending on the ultimate end use that you want. So you have thermal conversion, and so you can basically take different types of feedstock, you process it to get it ready for combustion, and so that might be, you know, shredding it up into fine materials, making sure that the water content of the biomass has been removed so that it combusts more readily, and you can do that to create power, to create heat, and to create steam. There are conversion processes that will turn your biomass into different sorts of end products. So torrefaction, gasification, and pyrolysis. So this can create biocoal, syngas, which is synthetic synthetic methane or other sort of synthetic hydrocarbons through gasification. Pyrolysis is a way that you can make charcoal, methanol, other sorts of syngas, bio oil. That process is it's kind of like combustion, but it's in the absence of oxygen. So it's like heating it up. If you ever go out to create a campfire, all the flames on the outside is like combustion, but on the inside of the wood, oftentimes you're getting some pyrolysis that's creating charcoal. That's through, if you think about like the embers that are being created when it's like red hot, but there's no flames, that's oftentimes an indication of pyrolysis. There's biochemical conversion, where you are converting to ethanol. This is actually what I was doing when I was an undergrad working in a lab, doing pre-processing of lignocellulose, and that often is through processes like fermentation. So uh, commonly known as to create alcohol, right? But that ethanol is sort of in the same way. But you can also create this with strong acids and strong bases to dissolve lignin in the cellulose. You can use ionic liquids. So there's a number of processes that allow you to turn the cellulose into sugars, and then you do some kind of fermentation process to create ethanol. And then lastly, you've got chemical conversion. So this is chemical transformation into things like biodiesel. So there's a whole slew of different conversion processes that lead to different end products. And yeah, I'm going to sort of leave it here. I think that biomass in itself has a huge amount of further material and sort of cycles and processes that we could go through, but for the purposes of this class, we'll sort of leave it at a high level for now, and we'll talk a little bit more specifically about sort of policy implications of a lot of these processes and biomass in general. I think the United States in particular has a lot of sort of interesting process or policies that are pretty relevant for this specific fuel type. Okay, so the last bit we'll talk about with potential is thinking about economics. So what does this look like? Actually, even before I talk about costs and prices and that sort of thing, I think it's kind of interesting to take have some perspective about the direct and indirect jobs that are tied in with renewable energy. And so this is a sort of overview across different countries in the world, different regions, as well as all of our essentially different renewable energy sources and sort of the number of jobs associated with this. So do note that these are in the thousands. So when I look at the sort of bottom total across the whole world for all of my renewable energy resources, you're talking about on the order of 7.5 to 8 million direct and indirect jobs in renewable energy. Of course, these jobs vary quite a bit from the production of the materials all the way to the creation to the actual production of the technology, and then the installation and the transportation, all of that, and the types of jobs are going to be pretty different as we go from one sort of renewable source to another. But this gives you some sense of the size and number of jobs. Really sort of thinking about, so this is a sort of different diagram, but similar in that it's just aggregating up across all the countries. So I guess the numbers will vary a little bit depending on who's counting and how you do the allocations. In fact, right, this number is already a little bit different from the last slide. So they're saying 10 million jobs, but you're getting sort of on the order of magnitude, right? 10 to the seventh number of jobs. When we compare that to other fuels, so fuels that aren't on this list, right? So thinking about things like fossil fuels. So the coal industry employs approximately 77,000 people, and that number is continuously dropping as coal sort of starts to fade away. And so just the solar industry itself, despite the fact that the technology can be relatively expensive compared to coal, and it's quite a bit smaller, right? The total amount of electricity being provided by solar versus coal is basically an order of magnitude different, it still actually is employing more people. That's not the same case in China, where you got about half the number of people employed for solar versus coal, which is 5 to 6 million. But that number in itself is also falling really, really rapidly. So actually this number, I think, was a 2017 or 2016 number. And so I haven't checked what the numbers look like now with both decrease in coal installation and usage, as well as technology improvements. But I expect that it would be definitely quite a bit lower than the 5 to 6 million from before. Okay, so thinking about costs. So I've shown this diagram before. And this is related to what we've learned, and actually what you guys have already done on the homework, in terms of getting what's called the levelized cost, which is the sort of most standardized way of comparing apples to apples, right? Because when we're talking about, oh, what's the affordability and the price of like a solar plant compared to a gas plant, it's really hard to compare, because or like a coal plant, right? Because like a coal or nuclear plant could take a decade to build. It's operating on the order of 1,000 to 2,000 megawatts, so it's like a 1 to 2 gigawatt system. So it's a lot larger, and the capital is just orders of magnitude different. How are you supposed to compare that against like a small solar plant, a solar facility that might be on the hundreds of megawatts instead of thousands of megawatts? So by levelizing the cost, it's not the perfect way, but it's a nice standardized way of being able to compare the cost across different technologies. So there's definitely uncertainty about this, and even this chart looks a little bit different than what was projected, right? Because this is a 2020 projection that was made initially in 2015. This was put together actually by the National Renewable Energy Laboratory, NREL in Colorado. But you can generally see, okay, what's the cost of any particular resource in terms of dollars per megawatt hours. And so the lowest is geothermal, and then combined cycle, then you've got wind. And that's actually been a pretty important comparison. You can see how close they are. Over the last couple of years, wind has sort of surpassed natural gas in terms of being cheap. So the prices are lower, which means, really at the end of the day, when I think about how to promote a renewable resource against like a fossil fuel resource, really it comes down to the economics, right? You can incentivize them with the government. You can have requirements to install some renewables. But at the point that it becomes cheaper than its competition, it'll happen by itself, because that's how you make money. And that's what's going to attract investors and people who are looking to enter the power production game. Now you would prefer to do wind rather than natural gas. So that's been a sort of important switching point. So past wind, hydro, and coal. Coal used to be cheaper than natural gas until fracking came around, and since then there's been this really dramatic shift towards natural gas, which we've talked about many times. But that definitely has to do with the economics, right? And not only is it causing more natural gas plants to be built to replace coal plants, it also is causing natural gas plants to be used more often than existing coal plants. And we'll talk more about that in our when we think about how the electricity grid works. Nuclear is fairly cheap compared to a lot of the other energy resources and pretty large. But there are several other sort of related to cost, but not directly issues with nuclear. And we'll have an entire lecture or half a lecture on nuclear power on Monday. So we'll dive a lot more into the issues surrounding that in a little bit. And then you've got solar up here. Wind offshore is a little bit more expensive. And so that's why you see lower volumes of that. And then there was, right, a question in chat earlier about why we don't see so much CSP. And I had briefly mentioned that probably the biggest reason is economics. It's just more expensive. So you would prefer not to do it. And we can definitely see that here, right? So this is the highest sort of thing on the chart compared to solar PV down here. That is kind of a static view of the prices. And so when I mentioned that, hey, you know, those projections were being made in 2015, but in fact, they may look even lower today. And we've seen a pretty steady trend where you're able to get to where essentially as we install more solar, the prices continue to fall. Okay, and so why is that? So the supply chains for the materials for solar are becoming more developed and sort of streamlined, so it becomes cheaper. The process with which we build them, we are getting more familiar with it. We're refining it, and it's becoming more efficient. That causes prices to fall. You have something called what's it called? With benefits of scale, essentially. So as the production process increases, not only is it having to do with the efficiency, but you produce things at larger volumes, and the throughput of the machinery and the production process basically becomes cheaper as you have larger amounts being produced. Yeah, economies of scale. Sorry, totally brain farted. Thank you. Economies of scale. You know, one of the things that I will mention is that, like, do be wary of the sort of prices that you see. So on the left here, I would say the bigger kind of takeaway from this is that the actual trend that the price falls. It's actually pretty kind of controversial when people talk about what prices are. You may have heard of things like grid parity for capacity of photovoltaics, and that means, like, at what point is solar power or even any other sort of renewable sort of on par with the average cost of capacity on the grid. But that's actually a different type of metric than LCOE, the levelized cost of producing energy, because oftentimes that's just talking about capacity. And so what I'm referring to is, yes, it may be like cheaper to install solar on a capacity basis. So when I look at 100 megawatts of like a coal plant versus 100 megawatts of a solar plant, those costs are now way more comparable. And in fact, the solar photovoltaic may actually be like cheaper on a capacity basis, but you have to remember, right? A coal plant or a nuclear plant might be on like 90% of the time, whereas a solar array may only be producing electricity maybe 20% of the time. And so on a pure like theoretical amount of capacity in terms of how much energy it can produce, they might be comparable, but in fact it might be producing 4 times as much electricity. And so you should always be careful when you hear about these things in the news about, hey, solar is like cheaper than, gas now or something like that, you need to keep in mind that they're oftentimes talking about capacity, and that a much more sort of apples to apples comparison is thinking about over the lifetime of your asset how much electricity is being produced. And that's where, if I'll go back one slide, that's where this slide I think gives a better sense of like apples to apples comparison of the actual cost of the technology. So do keep that in mind. So wind generation and economics. So similar story here, right? Wind cost has decreased quite a bit over time. And so notice that this one is in dollars per kilowatt hour, so dollars per unit of energy. So this actually is a levelized cost metric. And that's sort of right alongside corresponding to wind capacity growth. I guess I haven't talked so much about how these costs relate to electricity prices, right? And so maybe I'll just jump back here. So this is in dollars per megawatt hour, and the one that I showed for wind was in cents per kilowatt hour. So you're essentially just dividing by 1,000 here. And to give you perspective, so like this line right here, $100 per megawatt hour, that's about 10 cents per kilowatt hour. And for those of you who are paying your electricity bills, you may be sort of now familiarizing yourself with the sort of order of magnitude costs. So if you live in Davis, you are paying most likely a tiered rate in PG&E. Actually, you're probably on Valley Clean Energy, which is administered through PG&E. And the tiered rate, I believe right now, is 17 cents per kilowatt hour on your first tier. And then I think it goes up to like 21 or 22 cents per kilowatt hour in the second tier. So relating what you pay for electricity to the prices here, you're paying probably around 17 cents right along here. Whereas, wind is close to about 5 cents. The reason why you're not paying exactly, the marginal cost is actually, that's only a portion of your electricity cost. We generally like to say it's 1/3 generation, 1/3 transmission, 1/3 distribution. And I know we haven't covered this yet, but the big transmission lines are the big metal ones that you see on the freeway, that are really tall, big and metal, very high voltage. Distribution are the distribution infrastructure are all the like wooden poles that you see around town, and the transformers, and you may have even seen like the substation down on I think it's on let's see, L Street and L and is it L and 3rd, L and 2nd, something like that. So when it comes to what you pay for electricity, about 1/3 of it are these prices right here, the electricity generation, and then 2/3 in sort of the infrastructure on the ground that transfers the electricity to you. So the costs of entire projects sort of vary by region and size. So this is for wind power. You can see that it's decreased over time, and you can see this is a nice little handy graphic. It's a little bit confusing to read, but it tells you a lot of information. So these dots are individual like wind farm projects, and it tells you the total amount of capacity that's installed across these projects. And then it tells you the average project size, right? Back in, so actually this is actually a time slice for one entire year in 2016. And so you can see the number of small projects, there are 7 small projects that are like less than 5 megawatts. And then there are 13 projects that are quite larger than 200 megawatts. So there's a pretty big distribution of wind farms being installed these days, ranging from small all the way to quite large. Um, okay, biomass energy potential. So thinking about it from the economic viability. Um, so there are regional supply curves that differ quite a bit, that we're not actually going to get too much into. But I think more of what I wanted you guys to get out of this is thinking about the difference in global potential for biomass production. So thinking about what we're able to do theoretically, what we're able to do technically, and then now what we're able to do economically, which is definitely the smallest. So it's only 200 to 400 exajoules per year. And you can compare this against the number that was shown before. So this takes into the account the cost of producing the fuel and the competition of biomass versus other sorts of fuels. There's a huge amount of uncertainty that depends on how much like yield you think you're going to get, what you think the efficiency from converting the biomass into your electricity or fuel is, and then things like land use restrictions. Okay. So we will, again, cover in a lot more detail later on in class issues related to policies that are directly tied to renewable energies. And here I just kind of wanted to introduce at a high level some of the concepts and general policy mechanisms that we'll be thinking about in more detail later on. So there's a fairly wide landscape of policies, but you can kind of generalize them into two sorts of things. We typically, in like a public policy class, you might talk about how there are essentially two types of policies. There are ones where you're more rule based. So this is if you think of the analogy with a carrot and a stick, where the stick is like basically punishment or requirements for people, and carrots are more of like incentivizing people. We might think of the carrots as like a market-based mechanism, and you might think of the stick as like a regulatory requirement. So it's the same concept here. There are regulatory requirements to build and produce renewables and renewable energy. And for in the United States, one of the most common ones is known as the Renewable Portfolio Standards. It's also called the Renewable Energy Standards. And that's kind of at a state by state where we say, okay, you are required to build X number of or X capacity of renewables, or by 20. So in California, we actually have this thing where it's like, oh, by 2030, 50% of the energy that you produce has to be coming from renewables. Sorry, 50% of the electricity. There's a comparable one in the United States called the Renewable Fuel Standards that actually applies to biofuels, and again, that's something we'll talk about more later on. But both of these schemes are regulatory requirements for people to pursue renewables. The other sort of general set of policies are monetary incentives or support that really operate more through the market than as a regulatory requirement. And so these include things like feed-in tariffs, production and investment tax credits, power purchasing agreements, green energy credits, net metering, and then for biofuels, and actually also for electricity, low carbon fuel standards. Again, these are things that we'll learn a lot more later on about how they work, what's the design of these things. But this is to get you guys sort of oriented to understand that there are sort of two levers in which we can promote policies for renewables. In terms of policy support, this is sort of a high-level overview. this is actually worldwide, and there are basically a number of policies across electricity power for heating and cooling and for transportation. And there's some sort of breakdown in terms of types of policies. But this, again, is to give you guys just a rough sense of how much policies there are out there that are pushing forward these types of energy sources. We can see that roughly in a regional basis with this graphic here, countries with renewable power policies. And so a lot of the stuff that we see in the United States and in Canada are more sort of dependent on at the state and province level. Whereas you can see that most of the rest of the world, their countries are able to, I guess, get their act together and have federal regulation. Although I would say this chart is maybe a little bit deceptive. I mean, there's definitely some stuff at the federal level regarding renewable energy power, but I think it's not to the same extent as a lot of the other countries, which is why there is some differentiation happening here. So similar type of thing for renewable heating and cooling. I'm going to maybe skip forward a little bit just for the purposes of time. We've got biofuels for this one, but you guys can go back and look at this. It's more just to give you a sense of the regional coverage of these different policies. The one that I did want to sort of quickly hang up on is thinking about the Paris Climate Agreement. And so actually as you guys know, one of the groups is going to be diving a lot more into this. But it's a bit unfortunate, as you can see here, that United States is essentially the only country in the world that signed on to the agreement and is exiting the deal for now. We'll see what happens when we have a new president, hopefully in 2021. But you can see that there's pretty worldwide agreement as it comes to the Paris Climate Accords. And I'm definitely, I mean, I have done work on this in the sense of like transportation research that relates to emissions targets that like the Paris Climate Agreement has done, but I'm definitely pretty eager to hear about from the group more details of stuff that's coming out of the climate agreement. So that'll be good to hear at the end of the quarter. Okay, so the final set of materials that we'll talk about is environmental impact. Yeah, so I definitely went through a lot of material pretty quickly over the last set of slides. So you know, if you're having trouble retaining a lot of that information, you know, definitely make sure to review some of that material. You can go back and watch the recorded lecture since I moved through pretty quickly, but make sure that you are familiar with that material. Okay, so thinking about environmental impacts of renewables, when we compare the environmental externalities with stuff like the fossil fuels, it's really not that comparable, right? Because you know, the marginal emissions associated with renewables is really negligible compared to combusting a fuel and sending it up into the air. But that's not to say that just because I'm doing, you know, something like solar and wind, which doesn't have sort of marginal emissions associated with the production of electricity, that doesn't mean that there aren't environmental impacts and externalities. And this is, I think, again, sort of going back to the life cycle analysis that we've done, this is where that sort of thought process or approach really comes to take an effect, in that we're able to identify issues and environmental impacts that may be upstream of like electricity production, things having to do with the actual manufacturing of like the solar PV cells, of the material extraction, and so on and so forth. So a lot of the impacts from the environment are going to be situated around the production and end of use and recycling of these materials. So for solar energy, one of the big ones is that in terms of the amount of energy that it produces, the energy density is pretty low with respect to footprint when it comes, or pretty high with respect to footprint when comparing to like coal and natural gas. It basically takes a lot more land to produce the same amount of energy. And that can have, you know, ecological impacts depending on where you're putting them. For concentrated solar power, CSP, oftentimes I was saying that you are installing those in hotter areas, in deserts, right, which helps with the efficiency of boiling the water. But that actually requires a lot of cooling material or cooling water, which is kind of scarce in a desert environment. And then the materials, manufacturing has a lot of hazardous materials: arsenic, cadmium, even silicon dust. These are all carcinogens, and can also cause respiratory illness. So these are types of things that we think about along the sort of full life cycle of solar. Environmental impacts and externalities of wind. I'd mentioned this last time. One of the big ones is this issue called NIMBYism. NIMBY, NIMBY, stands for not in my backyard. And so that has a visual impact that a lot of people dislike. And actually that does play a pretty big role in the ability of power producers to install wind farms in certain areas. It can be loud. There's a lot of literature and study about ecological impacts with like wildlife disruption and bird collisions. And yeah, it's totally true. Kills lots of birds, and definitely can have an impact on the ecological system. But I always felt like that's somewhat of an unfair characterization, because if you look at the number of birds that die from wind turbines versus the number of birds that die from coal plants, it's like way smaller. And so yeah, there are these ecological and environmental externalities, but as I understand, I'm the ecological impacts of these things can actually be lower than a lot of the other ones that people don't talk about. Hydropower, there's lots of impacts on ecological factors, and so by damming reservoirs, you are really sort of changing the aquatic environment and the ecology that's related to that environment, and so that's one important thing to consider. And there's also issues with flooding. So reservoirs can, when you release large amounts of water, it can inundate areas of forest, farmland, wildlife, occasionally even towns, right? If you guys remember from, I believe it was last year, the Oroville Dam disaster, things like that can happen. And so there are definitely externalities associated with the use of hydropower. And then the last one that we're going to talk about is with biofuels. And so there's a pretty big range of environmental concerns with feedstock and production pathways, but there are some benefits as you transition to these types of things that help improve like energy security and local air pollution. Nevertheless, I think with biofuels, even more so than the other ones, uh, because of the way that we use the land, the impacts on environment and agricultural systems is quite a bit more uncertain. And there are these like large displacement effects, such as like, oh, if I decide to have a policy to promote biofuels, maybe that ends up leading to like deforestation of the Amazon in Brazil to make up for like lost food production, something like that. These impacts are a lot harder to tangibly measure. And so a lot of those externalities, there's a lot of studies and literature to look at these sort of impacts, and they're characterized with a fairly broad range. To make them sustainable, it definitely will require careful thought about policies, not only regarding forestry and agriculture, but how we actually decide to produce the crop without sort of impacting larger networks of systems. Okay, so we'll end here for today. Yeah, I guess we're sort of right at the end of time. So we'll end here today. On Monday, we'll talk about nuclear and go over the practice midterm, and then on Wednesday, we'll follow up, and we won't have a lecture, and we'll post the midterm, which will be a 24-hour test, and I will make an announcement of that on Canvas. In the meantime, I will hang around just for a couple minutes in case there's any questions about the class or about the material that we talked about today. Thanks, everyone.